So.
It's because we got a new code.
Yeah. All right, here we go. Today we want to talk about maximums and minimums. You already know a little bit about this. A critical number of a function is a number C in the domain such that either one of these two things happens. F prime of C does not exist, or F prime of C is equal to 0. Critical numbers are important whenever the derivative doesn't exist or wherever the derivative is equal to 0. That's really, really, really important for us. So we look right here. Let's start at this one right here. So this is C sub 2. We say that this is a critical point. Why do we say that this is a critical point? Yeah, it goes from increasing to decreasing. So everybody say the derivative is 0 there? Yeah. So we call that a critical point. Anybody remember why we call this a critical point? It's a corner, yeah. Yeah, the derivative does not exist at a corner, right? So this is a corner. I'll write corner there, whatever. And then derivative is equal to 0 again, right? Yeah. And then derivative is equal to 0 there. And then we call these critical points as well because they're endpoints, and you can't take the derivative at an endpoint. Endpoint are always critical points as well. Yep. The endpoint exists. The derivative at the endpoint does not exist. Very good. Okay. So those are some pieces that we have there. Okay. So we have these different ideas, such as an absolute maximum. Another way to think about this is the global maximum, the largest value on the graph. So you tell me when I get to the largest value on the graph. Yeah, this is the absolute maximum. So it happens at C sub 4. Okay. And in order to figure what that Y value is, we would just plug that in, right? But it happens at C sub 4, okay? You tell me when I get to the absolute minimum. Yep, C sub 1. I'll just write x equals C sub 1 instead of writing as a point. X equals C sub 1 is where the absolute minimum happens. But then we have these things called local minimums and local maximums, okay? And that means where it's the biggest or the smallest point right around that general area. And so we would say that this at C sub 2 is a local maximum.
So that would be like the second biggest?
Yeah, we don't really care which it is, just as long as in this general area it's the largest. And then we would say C sub 3 is a local minimum.
Oh, so it's relative to all around? Like relative areas? Like
Yeah, right around it. You know what I mean? Within its kind of immediate space right around there, you can see it's the smallest value.
okay, so probably be the middle of the graph.
You know what I mean?
We're gonna put all the locals down.
And then, how about C sub 4? Yep, we call it a local maximum. So notice that C sub 4 is a local maximum. It's also your absolute maximum. Okay. And then it looks like C sub 5 is a local minimum. Okay. So local maxes and local mins are something that's super important to us during this work. Absolute max and absolute min are concepts that come up a little bit more in the AP exam. We will get to them. Yes, sir?
So the certain point on the graph can be both an absolute and a local?
Yep. This is an absolute max and a local max.
Okay. So
Yep.
That you don't right?
What's that? Nope.
I'm confused with the local. I don't.
So this is the general idea for a local max or local min. Okay, if as you draw a box around that general area, if it's the largest or smallest value in that general area, then it'll be a local max or a local min. Okay. Now I know that makes people uncomfortable. You're saying around that general area. It's like how big of a box should you draw? It actually really doesn't matter so long as you draw, you know, any type of box around that area. So, you know, in this situation, suppose I draw a shape that looks like that. It's pretty easy to see that, you know, we have a local max there and a local min there. Well, what if you draw a function that looks like this? That has a ton of local maxes and local mins. You know what I mean? It doesn't have to be a big box. It can be a small box. So draw a very small box right there. You can see you got a local max right there. You know what I mean? So, but this is more of kind of what we're going to be dealing with is the nice behaving functions. Okay? So let's get to the algebra of today. And Fermat was a great mathematician, and he added this idea. It says if f has a local max or local min, and if f of c exists, then f prime of c is equal to 0. And here's his idea in a very basic form, okay? He says, suppose you have a function that looks like this, okay? Local max, agreed? Is the derivative equal to 0 there? No, because the derivative does not exist at a corner, right? So he says, I'm not talking about graphs where the derivative can't be calculated. He says, I'm simply talking about these kind of graphs. Talking about nicely behaving graphs. He says, if there's a local max, which we would agree is right here, right? Then he says the derivative must be equal to 0 at that spot. Make sense? And knowing that the derivative is equal to 0 at local max or local min is super helpful. So let's find some of those. First, let's look at some examples of some critical points so you can get used to this. As we determine critical points, you might find a critical point there. You might find a critical point there at general local maxes and local mins because the derivative is equal to 0. So those are times where it's say, hey, those are the really nice examples we're referring to. It is possible, though, that the derivative is not equal to 0 and still have a critical point. And we mentioned one that you guys talked about, and that was if you have what is called a corner. So this is a critical point where, in fact, the derivative is not equal to 0. Maybe remember from something we covered before that another time where the derivative does not exist is when you have a vertical tangent. That was on one of your tests and in some of the work we did. So if you have that kind of a shape, we would say that that is a critical point as well, because you have this vertical tangent that exists there. Okay. So once again, most of the time you find a critical point, it's going to be a local max or local min. But sometimes it might be a corner or a vertical tangent. Now I left this one off, and that is if the function is undefined. Now you could say that at that spot, some people are like, well, you have a critical point of that spot. Suppose that that function is the function 1 over x plus 2. For what value is that function undefined? Close. -2. Everybody agree? -2, it's undefined. So -2 is not part of the domain, is it? Like the domain of this function would be -infinity to -2 union -2 to infinity. It would not include -2. So while we say that it may seem like there's a critical point there, you can't say that you have a critical point for something that's not part of the original domain. Does that make sense? I guess it's not even a spot that creates a value. So it is not, because it's not part of the original domain. Right, and I'm not going to get real critical with you on that. I just want people to understand sometimes the confusion comes up. It does lead to some things later on. Okay, so let's try a couple of these. It says find the critical numbers of the function. So all we need to do is just figure out if there's a corner, or if there's a vertical tangent, or if the derivative is ever equal to 0. So I just simply take the derivative, and what do we get? Great. So the critical points would exist wherever that's equal to 0. Does that factor? What if it didn't factor? What would you do? Very good. You'd use the quadratic formula that Mr. Gens wrote in a program for your calculator, right? You just plug that in and that'll produce two values for you. So you can find it right on my YouTube page if you need help with that. So looks like I have critical points of positive 1 and positive 1/3. Those are the solutions. So we could expect that if we graph that, we would find local mins and local maxes in those situations. Could we graph it and find it? Sure. You want to do it right now? Take out your calculator.
He did it together with us. Do you think that have I stole this
Now, just to be clear, I'm glad Ella actually raised this question because this is something that comes up for students a lot. People look at this and they're like, well, which one do I graph? Do I graph the derivative or the original function? The derivative is telling us something about the original function. So I'm going to graph the original function so I can see, does it have a local max or local min at 1 and 1/3? I'm going to look at this graph, and you can see by the graph, it doesn't really look convincing there, does it? But maybe if I take my window and I change the window to a y min of -2 and +2, it will shrink that. Maybe I'll see a little bit better the behavior of this graph. Ooh, that looks a little bit better, doesn't it? In fact, if I change the window even again and I go -1 and +1, maybe I'll see even a better definition of the shape of this graph. Does it look like as I move my cursor, does it look like it might have a local max around 0.33? Yeah, it looks like my tick marks are just a little bit off. If we change the window again and went, say, -2 to +2, I bet we could get a really, really good view of this graph. And as we look at this, you can see, as Ella's helping us look at, 0.33, there we go. As we move over our other spot of +1, that's where we have critical points. So it's confirming the information about the graph. Okay, next one. F of x is equal to x squared minus 1 over x. Tell me the domain restriction here. X cannot be what? So we will not include 0 as part of our critical points if it so comes up. What would we do in order to find this derivative? Quotient rule. So f prime of x is equal to, so really all you're really doing today is just taking more derivatives. So there's not a whole lot that's really new there, but we are trying to determine these critical points. Derivative of the top, somebody. 2x times x. Yep, we'll do that. Minus. Did you say slow your bowl? Like, oh. I thought you were like referring to her brain as a bowl. So f prime of x is equal to, in the top I get what? 2x squared minus x squared would be x squared. And then it would be plus 1 over x squared. So when I look at something like this is a little bit new. I want to look at where the top is equal to 0, because that's where it would be equal to 0. I want to look at where the bottom is equal to 0. That's where it would be undefined. Where's the bottom equal to 0? And that's not part of our domain anyway, is it? So we're not going to list that. Is the top ever equal to 0? Do you agree the top is always positive? So this derivative is never equal to 0, is it? So that means that the graph would never have a local max or local min. since Ella brought up our curiosity, I'm just going to plug it in and see if that's right. Because, you know, I like a way to confirm my answer. Right now, I'm like, boy, why would I have written that problem if it really doesn't have a local max or min? And maybe I was trying to think of bringing up that point. Oh, does this ever have a local max or local min? No, it never has a derivative equal to 0 that way. So that confirmed it for us.
So what's the answer?
No critical points. And by the way, this is a 2-day lesson. We won't finish it one day here. An absolute value function. Does anybody know what it looks like? Very good. So this looks like this. So true or false, this will have a critical point. The critical point happens where the corner happens, agreed? And if we look at this, if I take this function and I don't even take the derivative, if I just factor out a 3 and write it as x minus 2, does everybody agree that this function is just shifted to the right 2 units? So if I were to graph this shape, it would be right 2 units, and it would look like that. So for what x value is there a critical point? X equals 2. So I didn't even try to find the derivative because the derivative does not exist for a corner. I just found out where the corner happened. Yes? Because the top is never equal to 0. The top is always positive. Yep. Yep. Okay, so let's look at one that we get wrong on the test. Okay, so this is one where people make this mistake all the time. Everybody understand why people might get something wrong there?
Yeah.
So we need to take that derivative. Let's go back and see if you know how to take this derivative. What do you got? Excellent. X to the 3 halves minus 2x to the 1 half. Okay, so I think we all understand that while we could do some of these things before, we don't always retain that information. That's why people make mistakes on this test. So let's try to clean that up as you're working through this. All right, so I take the derivative. So the derivative is 3 over 2 x to the 1 half, yep, root of x, minus x to the negative 1 half power. Yep, because 1 half times 2 is 1, and there I have it. So what I'd like to do is figure out where this is equal to 0. So in the top, I have 3 roots of x over 2 minus, and this reads as 1 over the root of x. And the best way to look at where this is equal to 0 or where it's undefined is, in fact, to create one fraction. If I want to create one fraction, what do I have to have? Common denominators. So please pay attention. This may look a little bit different too, but I'm going to multiply top and bottom by 2 and multiply top and bottom by root of x. So I have 0 is equal to, what does this become here? 3x minus 2 over, what's the denominator? 2 roots of x. Okay. Is the top ever equal to 0? Yeah, for what value? Where is 3x minus 2 equal to 0? Yep, x equals 2/3. Is the bottom ever equal to 0? Where? At 0. And if you look back at the original function that we have, you can see that the domain is x greater than or equal to 0. So 0 is included. We don't include -1, we don't include -2, but we do include 0 and everything that's positive. You can take the square root of positives. So we list 0 as one of those options. Let's go back here and let's just check and see what we get. If I plug in y equals, and I take the square root of x to the 3rd power, close that close that parenthesis, and I minus 2 roots of x. Let's see if we get the graph that we want. Struggling there. Graph. So I should have a critical point at 0 and at 2/3. Let's zoom in a little bit on that and see what we get. I'm going to create my y min to be a -3, my y max to be a +3. I'll look at that graph again. And I'll even change my x values to a -4 and a +4. And you guys tell me, do you think, does it look like that local min is at about 2/3?
Yeah.
It sure is. And then what's the other spot for the critical point? 0, because that's where the graph starts. It's an endpoint. In fact, if I look at the format and I get rid of my axes, I take my axes off, you're going to actually see in this situation the graph where it just has an endpoint right there. And the mathematics found those, which is kind of neat, isn't it? Question, sir.
0 there.
0 will give you 0 in the denominator.
Okay.
So we're going to pause there. I'm going to hand you the worksheet. I'll give you the rest of the homework tomorrow. But you are finding these critical numbers. You've seen 4 examples. I think that Friday is a reasonable goal for my friend Maddie to take the test. However, if that doesn't work for her, I would just ask that she come and talk to me and we figure something out. I realize that my class is not your only class, and I also know that when you're homesick, you don't always feel like doing work. Because you're sick. Totally get it. I would just like to help you and have a plan in place.
It should be before and after school, correct?
No, so Maddie has a study hall 7th hour. So she's going to come in 7th hour and take it.
How about 4th hour, does that work?
You have what lunch? B lunch?
Yeah.
So who do you, I have, but I could give it to your study hall teacher. Who's your study hall teacher? Right. That would be best. I don't like breaking up the test into 2 parts. If you had A lunch. Right. What? Sure. Yeah, Kendall said, could she take a day of class and take it during class? That's fine as well. Just watch the video. Tomorrow after school? I think that would be fine.
Or during study hall, I don't know.
I think so.
I'll either do that or
How's he doing? I know he did well. I just he had his wisdom teeth.